There we go. Now we're only 12 minutes late. That means I have to talk fast. Okay, so next exam 5 is going to be on Chapter 9, Chemical Quantities. And regain control. There we go. There we go. Chemical quantities. So we're going to look at particular mole-mole relationships, and those have to do with the balanced equations primarily. And then we're going to look into mass calculations, and that's got a fancy term called stoichiometry. But I'll give these things to you in detail. So rather than define these things, let's get on into the meat of the subject here. Okay, when we have a balanced equation, and we've done those, right? Yeah, we did those in Chapter 8, I think. When you have a balanced equation, for instance, if we were to say burn methane, and that would give us carbon dioxide and water. Okay. So let's see if I can do this without setting up a budget. Carbon, 4 hydrogens, 2, 4, 2. So that should be balanced. 1, 4, 4 oxygens. There's 2 there, 2 there. Yeah, that's balanced. So what that means is, on the microscopic level, it would mean that 1 molecule of methane reacts with 2 molecules of oxygen because it's diatomic, and produces 1 molecule of carbon dioxide and 2 molecules of water. But it also means on the macroscopic level, if you have 1 mole of methane, 6.022 times 10 to the 23rd molecules, 1 mole of methane, 2 moles of oxygen combined to produce 1 mole of carbon dioxide and 2 moles of water. So they're both valid interpretations. The one that's useful for our calculations is the latter one, where we talk about moles, because we know that 1 mole has a defined weight. Right? For elements, it's this number right here. For compounds, it's a combination of 12.01 and 4 times 1.01. Give you the molar mass of methane. So if you know moles, then you can interpret that in terms of masses. Okay, so that's what the coefficients mean. They mean moles. And if there's not a number out here, it's a 1. Okay, just I'm going to hammer that topic. It's just because there's no number there doesn't mean there isn't a number. We don't write the number if there's just 1. If you've got a formula there, then there has to be at least 1. Otherwise, you wouldn't write it. I mean, we wouldn't write it and put a 0 out front. Right? That would be stupid. So don't forget those. If there's not a number, it's automatically 1. Okay, so in this example, we're actually, this is ethanol. We're burning ethanol. That's what this compound is right here, ethanol. And whenever you burn a hydrocarbon or a carbohydrate or a compound, an organic compound, usually you end up with carbon dioxide and water. So you might notice that trend as we move along, looking at different possibilities. This equation is balanced already, which just means, for review, that you have the same number of atoms of each element as products as you do reactants. Okay. So there's the interpretation. And 1 mole of these, those 3 moles of oxygen yields 2 moles of carbon dioxide and 3 moles of water. Okay, so here's an unbalanced equation where we have copper 1 sulfide plus copper 1 oxide. And the product is copper, metal, the solid, plus sulfur dioxide. So this is the balanced equation. Right? One of these plus 2 of those yields 6 of those and 1 of those. Okay. This is typically what you see in a smelting operation. So you'll have these compounds in the copper ore, and all they have to do is heat it up. And it reacts and produces copper metal in this byproduct. So if we balance the equation, how many dozen copper atoms could be produced from a dozen molecules of sulfide? And well, let's see, what are we saying? Let me get the balanced equation up here. The words don't tend to be meaningful for a chemical reaction. Things work much better if you have a balanced equation to talk about. Okay, so there's our balanced equation. Now what are they saying? Let's see, how many dozen copper atoms? So we're looking for how many dozens of those could be produced from a dozen molecules of sulfide. That's this one. So we got 1 dozen here and 2 dozen oxide. Okay? So what's the relationship here? For every one of these, you need 2 of those. Right? So we have 1 of those. It's 1 dozen, but it's still 1. We're using the same unit of measure here. So this is the ratio, 1 to 2. It can mean 1 to 2 moles, but it can also mean 1 to 2 dozen. And as long as the unit of measure is the same on this side, then 1 of these plus 2 of these yields 6 of those. It's all the ratio, the number ratio. It's 1 to 2 to 6 to 1. So what does that mean? Well, if you have numbers of something here, let's just say we have 3 moles of this one. How many moles of that one will be produced? 3. Because you've got a conversion factor built into the equation. The conversion factor is composed of the coefficients. Right? So for every 1 of these, you get 1 of those. Okay. All right. So what do we got here? Looks like we're splitting the water molecule into hydrogen and oxygen. So that's a decomposition. And this is just an artist's idea of what's happening. 2 water molecules and yield 2 hydrogen diatomics and 1 oxygen diatomic. And we're balanced, right? We got 4 hydrogens here, we got 4 there. We got 2 oxygens here, we got 2 oxygens there. So we're balanced. We would be just as easily balanced if we had 4 of these. It would give us 4 of those and 2 of those. Of course, this is not the standard format for writing a balanced equation, right? Because you can divide this whole thing through by 2 and simplify it. So this is the simplified version, and this is an expanded version just to make a point that the ratio is still the same. Okay. So that's the concept of the mole ratio, and we derive it from the balanced equation. The mole ratio gives us a conversion factor. So if we know how much of one component we have, we can determine how much of the other component is required or produced. So if it's on the same side as the reactant, it would be how much is required. It's on if the answer we want is on the right side of the arrow, it would be how much is produced. Okay, so let's use this one as an example. Sodium silicon fluoride. Okay, and plus sodium. And they've been kind enough to balance the equation for us already. This produces solid silicon and 6 sodium fluoride. You ever seen a picture of pure silicon crystal? They grow them for the semiconductor industry, right? Those little chips that they build for your phones and computers. They have to start with pure silicon, and they create a single crystal that's about this big around and about 10 feet long, and it's round. And then they go into their clean rooms, of course, and they slice it and make these circular wafers. And they build the chips on those pieces of pure silicon. I don't think this is the way they make it, right? But that just triggered a thought. Okay, how many moles of sodium fluoride will be produced? So this is the one we're looking for. If 3.5 moles of sodium, 3.5 moles of sodium are reacted with excess here, right? So we're never going to run out of this one, but we have a limited amount of this one. So we're going to say if we use up all of this one, how much of that one are we going to produce? Right? So we have 3.5 moles of this one. And at this point, just don't get confused with that number. That number doesn't go in here yet. We start off with this one. That's what we begin with. Then we say, all right, we need to cancel out the sodiums, right? So it goes down here. And we need to end up with the sodium fluoride. Okay. Then you look for the coefficients. They will provide the ratio here. So 4 sodiums related to 6 sodium fluorides. Right? So now we have 3 halves times this number should give us the answer. Right? That cancels. These is with sodium fluoride. So I get 5.25. Okay. There's our conversion factor. There's our answer. Any questions? Seems pretty simple. We're going to build on it though, right? So don't become complacent. Let's see. How much time we got? Where am I in the? Let's so what's the first thing we do? We check to see if it's balanced first. All right, so we have propane. This is propane. And we're going to burn it and produce carbon dioxide and water, just like all the other hydrocarbons that we burn, methane, butane in the cigarette lighters. Butane's got 4 carbons. And a similar reaction occurs when you burn it with oxygen. But it's a different balanced equation, right? Because you're starting off with a different reactant. But we check to see, be sure it's balanced, and it appears to be 3 carbons, 8 hydrogens, and 10 oxygens. So there's 6 and 4 is 10. Okay. So we know it's balanced. Then we look at the question. How many moles of carbon dioxide are formed? So that's the unknown. That's where we're headed. We want to know how many moles of that one. Where are we starting from? 3.74 moles of propane. So 3.74 moles here. We need to convert that to carbon dioxide. Right. So we start off with 3.74 moles, and we need to end up with this one, so it's in the numerator, cancel that one in the denominator, then we fill in the ratios based on the coefficients. So we have 3, 1, 3 here, and 1 there. Right. And the answer is 11.2 moles of carbon dioxide produced from this much propane. Okay. Okay. But the problem is, in reality, you're rarely given moles. You might be on a test. But if you're actually going to do this experiment in reality, you're going to start off with a certain measurable amount, like mass, right? And that's where we're going to start. We're going to start with mass. Even if it's a gas, we're going to use mass. So the first thing you do, well, actually, there's something you do before this, depending on the question. If it's a word problem and the names of the compounds are given, and the products, the reactants and products, you have to write those correctly, right? So if I said propane is burned to produce carbon dioxide and water, you would be within your rights to ask me what propane is, because we haven't talked about that. So I'd give you the propane formula. But you have to write the compounds correctly, then put them in their proper places in the equation, reactants and products, then balance the equation. So that's where we are here with this step. Balance the equation. Then you have to recognize that the balanced equation refers only to numbers, moles, as an example. Moles of this plus moles of that yields moles and moles. Okay, we're not talking about mass, we're talking about moles, numbers. If you start off with mass, then in order to use that balanced equation, you've got to convert to moles. So you need to know the molar mass of the compound to convert it to the mass to moles. Then you can navigate through that balanced equation. Okay, we're going to do an example, of course. Right, then you find out how many moles of product are produced or how many moles of reactant are required. Then, if the question calls for mass as an answer, then you got to convert back from moles to mass. And that requires another molar mass, a different molar mass for the other reactant or a product. Okay? So those are the steps. And here's how we're going to get there. Here's an example. Okay. So we have, in this particular problem, you're given the equation. So that was nice of them. Chromium reacts with oxygen. Right. And it does that extremely fast. So if you have stainless steel, which is various amounts of chromium are added to steel to make it stainless. The original amount was 35%, so it's pretty high. And you know that the steel doesn't rust. The reason it doesn't rust is it's got chromium in it, and the chromium reacts with oxygen instantly to form this oxide of chromium. It happens so fast that it forms a very thin layer right on the surface of the stainless steel. So thin that it still looks shiny. So this reaction happens extremely fast. You scratch the steel, it instantly heals with this reaction. Okay, now back to the question. How many grams of chromium-3 oxide can be produced? So this is the question. How many grams of that compound can be produced from 15 grams of that metal, right? And you have excess oxygen. There's plenty of oxygen. So they're doing it in the air. Or they could be supplying oxygen in a closed vessel. Either way, you got plenty. So we only need to be concerned with converting this to that. So think of this balanced equation, which is not balanced yet. Okay, so let's do it. Let's use our technique, right? I can do it in my head, but then I might be racing ahead of you. So chromium and oxygen are the only two elements we need to be concerned with. You got 1 here, 2 there. You've got 2 here and 3 there. So let's start with chromium. We need 2 chromiums. Okay, so that's 2. Now we need 3 oxygens. So how do we get 3 oxygens out of 2 oxygens, out of O2? Remember the trick? The fraction. Right? So now we got 3. So technically it's balanced, but we want to we'll follow convention. So we multiply the whole thing through by 2 to get rid of the fraction, right? That will cancel out the fraction. That will make this one 4. 2 times 2 is 4 still. In spite of new math, it's still 2 times 2 is 4. And this one is 3. And that makes this one 2. So we have 4, 3, and 2. And that one's been used up. Okay, so now we got our balanced equation. And think of the balanced equation as having these walls, these great walls built in. Here, here. You cannot cross that wall unless you're in moles. If you're in grams, you're stuck. You can't move. You got to convert it to moles, then you can navigate. Yep. Right. So 15 grams of chromium is how many moles? Well, we've got grams here and moles here, right? To convert to moles. So you go over here to chromium, 52.00 rounded off. Okay. So now 15 divided by 52 is what? 0.288. 0.288 moles. And that's of chromium. Now you've got moles. You can go anywhere you want to in that equation. We're going to convert moles of chromium to moles of chromium-3 oxide. So we need a conversion factor that will convert that to this. Right? So we got 4 chromiums, right? After we balanced it, there's a 4 here. And there's a 2 here. Right? So we just need half of that, right? 2/4 is still a half, in spite of new math. 0.144 moles of chromium-3 oxide. oxide. Is it chromium? Yeah, it's chromium 3. Now that you've got moles, convert back to grams. So we need moles on the bottom, grams on the top, and you need the molar mass of chromium 3 oxide. So 1 chromium is 52, so 2 chromiums would be that, and then 3 oxygens, which are 16 each. So we have 52, 2, and then 3 times 16 is 48, is 152. Grams per mole. So there's our new conversion factor. Grams per mole. Moles cancel. Leaves us with grams. So what would that be? 0.144 is 21.9 rounded off. Of chromium 3 oxide. So there's your answer. Okay, we already did that. There we go, there we go, there we go. There's our conversion from here to here. And then there's our conversion from there to there, only they actually that's this here. Okay. And then finally, our conversion back to mass. Okay, 21.9 grams. So those are the basic steps that you'll follow in every stoichiometric problem. In this case, we're starting off with grams and we're ending at grams. Okay, but it would be just as effective if we had a gas here and we were given a certain pressure and certain values. Well, not yet, because we haven't talked about. No, we haven't talked about gases. But when we get to the point where we're talking about gases, if you're given certain information about the gas, it doesn't have to be in mass, doesn't have to be in moles, but if you're given the right information, you can calculate how many moles of oxygen there are and go from there. But for now, we're just talking about mass. So mass here, convert to moles, then you can travel here, convert back to mass. Okay. So moles is your balloon. You got to get in the balloon, your mole balloon, and fly over the wall and reach your destination. Otherwise, if you don't have moles, you can't go anywhere. This is just a one-step conversion. I put that in the slide, but I think it's easier to understand if you do it step, 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 rather than all at once. Okay, let me see, I want to be sure we cover all our topics before we run out of time. Everybody knows the toothpaste has fluoride in it, right? You have to build strong enamel. How do they get it in there? They don't put pure fluorine in there because fluorine's gas, right? So you can't do that. You can't put that in your toothpaste. Besides, it's very reactive, so you put it in there and it reacts with whatever's there. So you need to put it in as a compound, a soluble compound. And the typical choice is 10,2 fluoride. You know you had 10 in your toothpaste. They might be using other compounds now. Ammonium fluoride, it's soluble too. But our bodies don't absorb 10 very well, so you can can swallow a little bit of it, won't hurt you. Okay, so here's how tin is produced. Hydrofluoric acid and tin metal makes tin 2 fluoride plus hydrogen gas. Right? So when that reaction occurs, you're going to have lots of bubbles. So what do they do with the hydrogen? I'm not sure. If there's enough of it produced, you know, they might scavenge it, use it for something else. There's a market for hydrogen gas if you make enough of it. But the question now is how many grams of tin 2 fluoride can be produced from 55 grams of hydrogen fluoride? Well, actually, it's aqueous, so they should have said hydrofluoric acid. As long as you have plenty tin, we're not going to run out of tin. So you go through the steps. You start here, because that's how much you're given, and you want to end up over here. How much can you get out of that? So you convert 55 grams of hydrofluoric acid to moles, and then you navigate to tin 2 fluoride in terms of moles, then you convert back moles to mass. And this is the single step, but here's our conversion to moles of HF, and then here's our conversion of that moles of HF to moles of tin 2 fluoride, and here's the conversion back from moles of tin 2 fluoride to grams of tin 2 fluoride. There's your molar mass of that one. This is the molar mass of HF. This is the molar mass of tin 2 fluoride. Step, step, step. For this one, we're interested in if we have 20 grams of phosphorus trichloride, we will know how much water is required to completely react with that, right? So in this case, we don't care about the products, not in this problem. All we care about is the two reactants. And the procedure is exactly the same. You convert the mass to moles, moles of one to moles of the other, and then convert back to mass. Okay? So here's where we convert phosphorus trichloride. Is it locked? You get locked out?
Yes.
That happens. Here's our phosphorus trichloride, and here's the molar mass of phosphorus trichloride. Remember, we've got to convert it to moles. So once we get moles of phosphorus trichloride, we can convert that to moles of water using this ratio. The coefficient tells you the ratio, 3 to 1. 3 to 1. And then once you have moles of water, you determine the molar mass of water and convert to grams of water. Okay, so same step, step, step as before. Only in this one, we only care about this side of the equation. We don't care what happens over there. Okay, I'm going to do this one on the board because it'll probably spin your head around. So let's say we have this reaction and they've been kind enough to balance it for us. This is an unknown element, right? Probably a metal, but it doesn't have to be a metal. Could be. And the chemist goes in the lab and takes a sample and reacts it with diboron trioxide and gets a product like this. Tetraboron trioxide, whatever X happens to be. And also that X combines with oxygen in this ratio. Okay, question is, what's X? Okay, what do we know? If we can determine the molar mass of X, then we stand a really good chance of finding out what it is just by searching the periodic table, right? We know that atomic numbers tell us exactly what it is, but there's no way we can get the atomic number out of this. So the next best thing is, what's the molar mass of the element? See, they're different too, right? They're not as definitive. Some of them come really close to one another, like argon and potassium are really close. But usually, if you know the molar mass, you can find out what the element is. So we're looking for molar mass. Remember, molar mass, which I abbreviate molecular weight, is in terms of grams per mole, right? So if we know the mass of X and how many moles there are, we can find out what its molar mass is. So let's see, is it going to give us some more information? Yes. That's 175. I wanted to be sure that wasn't a decimal. 175 grams of X, right, are reacted with diboron trioxide to produce 2.43 moles of this compound. 2.43 moles. Okay, what's the identity of X? So we've got the mass, right? We got that term already right here. We need to find out how many moles is it of this one. So can we do it from here? Probably, if that's a balanced equation. We know how many moles of this, so we can convert that many moles to moles of that. 2.43 moles of this one. And we need a conversion factor that will give us that. Right? So the ratio comes from the coefficients. Right? This is a 1. Don't forget that. That's a 1. And this is a 6. So 6 times 2.43 is 14.58. Moles of X. There we go. So molecular weight then of X equals grams per mole. Divide that in there. So I get 12.0 grams per mole. That's the molar mass of X. So you just go up here, and they get bigger from left to right and top to bottom. So if we follow along, stop at this one. That's the closest one. Nothing else comes close to 12. So X equals carbon. Okay? The key to this problem is understanding the definition of molar mass. You need grams, and you need how many moles that grams represents. If you can find those two terms, you can calculate molecular weight for molar mass and find out what X is. So then when you're given this, you just say, well, let's see, I've already got that term, set that aside. I'm given this, can I convert that? Sure enough, you can. Convert it to moles, you got your answer. Okay? That's critical thinking. Okay. So, what do we mean by a stoichiometric mixture? Maybe you know, maybe you don't. If you read ahead. A stoichiometric mixture is a combination of reactants in which after the reaction, there are no reactants left. They're completely consumed, both of them. So they have to be, in order to be stoichiometric, they have to be exactly the right number of moles of each one to react with nothing left over. Right? So if our reaction was, oh, I erased it already. If we had 1A and 3 B's to produce something, then we would have 1 mole of A and exactly 3 moles of B. That would be a stoichiometric mixture. No leftovers. And that virtually never happens. Right? Why? Because when you measure out your reactants, you do it on a balance. And measuring devices, they all have error. Right? You think you've got it right on the nose, you know. And I have students in my lab that look at that. The method called for 1.457 grams, and I got it right on the nose. Okay, that's nice. That's a skill, right? But the balance may be lying to you. Right? 1.455 is what it's actually giving you. So the moral of that story is stoichiometric mixtures are a starting point. That's our balanced equation. That's the stoichiometric mixture. But in reality, you're going to run out of one of them first and have leftovers. Here's an example, right? Nitrogen plus hydrogen yields ammonia. That's probably the Haber-Bosch process, right? If it's stoichiometric, then let's see, there's our nitrogens, the big blues, and there's our hydrogens, the little blues. So it takes 3 of these for every one of those. So there's 3 to 1, there's 3 to 1, 3 to 1, 3 to 1, 3 to 1. So that's stoichiometric, you know, on the molecular level. So you end up with 2 ammonias for each one of these pocket reactions. That's what the stoichiometry says will happen. But in this case, we've actually got extra nitrogens, right? You got enough hydrogens to react with this one, and that one, but these 2 are left out of the party. There are no hydrogens left for them. So they're still sitting there after the reaction. Those are excess. You got more than you need. Whereas the hydrogens are limiting. They're the ones that run out. Okay? That's the whole concept behind limiting reaction. One of them runs out first. And that nearly always happens. I think I'm pretty safe in saying that always happens. The only way you could guarantee this to happen is if you could get down to that size and pick them out one at a time and say, this is your partner, you go over there. This is your partner, you can't do that, right? We're on the macro scale. So limiting reactants are always an issue. Okay, so there's your definition. And in this case, the limiting reactant is hydrogen. It runs out. There's no hydrogen left on the other side, but there is nitrogen left. Okay, so how do we do calculations? Well, as usual, you need the balanced equation. Then you need to know how much of each reactant is given. And here's a clue. If you're given a word problem and it says so many grams of A are reacted with so many grams of B, right? If you're given 2 absolute values for each one of these, you can be pretty sure one of them is limited. If it says so many grams of A is reacted with excess, then you're off the hook. You got plenty of this one. You just need to focus on this one because it's going to be used up completely and give you product. But if you're given 2 absolute amounts of each one, now you got to figure out which one's limiting, because the limiting one is going to determine how much product you can produce. The excess one is going to be left over. Okay. So after you balance your equation, you write your compounds correctly, balance your equation, and then identify how much of each one you have. Then you need a method for determining which one is the limiting. Well, here it comes. This is our example. We're going to combine methane with water to make hydrogen gas and carbon monoxide. This is one of the reactions that they use to produce hydrogen for fuel cells from methane. We got lots of methane. But if we just plain burn methane, of course, we set the global warming hysterics teeth on edge, right? So we convert it to hydrogen. Okay, no carbon, we're safe now, right? But look at what all this carbon we produced over here, carbon monoxide. So we don't tell them about that. Look at all that beautiful hydrogen, and they're happy. So in this case, when we do the reaction, let's see, is this balanced yet? There's one carbon, there's one oxygen, and there's 4, 5, 6 hydrogens. It's balanced. Okay. So if we say our reaction is one methane, here's one methane, and there's one water. So those two together produce 3 hydrogens and 1 carbon monoxide. That's good. If we have one of these and one of those, okay, that produces this. No, these two, they're putting these two together. Those produce that, and these two produce that. We got this one left over. That methane has no dance partner. Okay. So methane is excess. All right. So you can read that at your leisure. I think it's more important, now that we have the concept, to actually go through an example and work out how to solve the problem. And I'm going to skip A's and B's. Right? They're useful sometimes, but I want to use a real problem. So let's see if we can find one. Nah, we're still A's and B's. Let's get a real problem. If it doesn't give us one, I'm going to have to make one up. Here we go. Well, okay, let's go ahead and look at this while we're here. This is our balanced equation for reacting hydrogen and oxygen to make water. Okay. Space shuttle engine. Which one of these produces the greatest amount of product? So the product is going to be water. If we have 2 moles of hydrogen and 2 moles of oxygen, how many moles of water are we going to produce? Well, which one runs out? This one, because it's 2 to 1. You got 2 moles of oxygen, you only need 1 of them, right? So this is the limiting one. So 2 moles of hydrogen will make 2 moles of water. There you go. How about this one? 2 moles of hydrogen and 3 moles. Same situation, hydrogen runs out. This one, 2 to 1, that's our stoichiometric ratio. That's a mixture that we've created theoretically. So it still produces 2 moles of water, but there's nothing left over here. Now, how about this one? 1 mole of oxygen, 3 moles of hydrogen. Which one of these runs out? Oxygen runs out. We've got 3 moles of hydrogen, we only need 2. So they each produce exactly the same amount of product. All right. I got to do something about these slides. Too many A's and B's in here. I need reality. Here we go. This is good. Okay, so here's our Haber process. Actually, it's Haber-Bosch. Haber came up with the idea before World War I, because the Allies were starving Germany for guano from Chile, which is what they used to make their gunpowder. Right? So Haber set about to figure out, how can I produce cheaply ammonia? Because if you got ammonia, you can produce nitrates, and nitrates are what go into explosives. All you have to do is oxidize the ammonia, and you can make it nitrates. So he figured this one out, how to do that. And then Bosch came along and refined it and made it better. So that's why we use both names. All right, so we got a balanced equation there. And we're saying we're given 3 grams each of these two. 3 grams. How much ammonia can you produce? All right. So you're given absolute amounts of each one. So the light bulb goes on, says one of them is limiting. So how do you find out which one's limiting? The simplest way is to convert both of them into moles first. Then take each one independently and find out, if I use all of this up, how much of that will I produce? So this one to moles, convert to that. This one to moles, convert to that. And the one that's limiting is the one that produces the smallest amount of product. So this 3 grams of nitrogen converted to moles. So nitrogen is 14.01 times 2 is 2802. Okay. So that's how many moles of nitrogen we have. Divided. So that's 0.1071. 0.1071 moles of nitrogen. Okay. Now, how many moles of hydrogen do we have? Need a different conversion factor. So how many grams is H2? Well, one of them is 1.01, so 2 of them would be 2.02. So 2.02 divided into 3 is 1.485. Hydrogen. Now we can use our coefficients to find out how much ammonia would each one produce. I mean, you've probably figured it out already, but we're gonna do it the long way, because it's the same method every time you get a problem like this. So this is nitrogen on the bottom, ammonia on the top, same here, here, there. So for every nitrogen, how much ammonia is produced? 2. Right? So 2 times this one is 0.2142 mole of ammonia. And this one is 2 times that, which is almost 3. Let's see. 116, 17, 189, 2.970 moles. Okay? So that's what would happen if each one of these were completely consumed. So which one's smaller? This one. The one that's produced from nitrogen is the smallest. So that makes this one limiting, and this one excess. Right? So to answer the problem, we want to use this conversion to ammonia. So now we have this many moles of ammonia. We can convert that to grams with the molar mass of ammonia. So ammonia is 14.01 for that one, and 3.03 for 3 hydrogens. 1704. So we just need 0.2142 minus 1704 times 3.65 or 3.6, rounded off, grams of ammonia can be produced. Okay? So those are the steps for doing a limiting reactant problem. Find out which one is the limiting one by converting it to moles, then to your target, and which one's the smallest. That's the limiting one. Okay? And there's your answer. I rounded off, but close enough for government work. Okay, any questions before we get to, I think this is our last topic. Pretty near, as they say. You ever heard of that one? You have. Pretty near?
No.
You've not heard of that one either.
You're too young today.
You can get a lot of these from Beverly Hillbillies. Just watch the reruns of Beverly Hillbillies. Yeah. I'm not sure all the ones that he's used. They ever use flickered and snot?
Yeah.
Yeah, okay. Okay, percent yield. So what do we mean by percent yield? The idea here is that if you use the equation, balanced equation, and you calculate, say you go from grams of one of the reactants to grams of product, that assumes 100% conversion from here to here. Okay, but that rarely happens. I mean, you're lucky if you can get 90%. Right. So if you start off with 10 grams of A, and you expect it to produce 20 grams of B by your stoichiometry, but you actually only get 18 grams. You lost something in the process. You know, it can happen in a number of different ways. Right. Then your percent yield is just the ratio of this one to that one times 100. Right? You expected that amount. Percent yield is the actual divided by the expected times 100. Right? So I gave myself a difficult one here. Let's see. 90%? Let me see if that's right. Yeah, 90%. Okay, so that's what that means. 90% yield means you got 90% of what you expected. Right? We expected 20, but we only got 80. So let's see, is it going to put the theoretical yield is this one, or expected yield is expected, or theoretical. And this is actual yield. Okay? It's a really simple concept. Now, like any formula, percent yield is equal to expected divided by actual times 100. You've got a value here, a value here, and a value here. If you know two of them, you can find the other one, right? Just like any equation. So you're not stuck with going only one direction. A, B, C, I don't like those. Maybe it's not going to give us. Okay, here we go. So this one asks you for the percent yield if you're given if you get 1.5 grams of sulfur trioxide from 1 gram of oxygen and excess sulfur, then what's the percent yield? That implies that 1.5 grams of sulfur trioxide is a smaller amount than you expect. So if we, let's see, when are we supposed to, 920? 40? Good. So we can finish this one. So here's your balanced equation: 2 sulfurs and 3 oxygens yields 2 sulfur trioxide. And we're right up here, what we got, 1 gram of oxygen, okay, actually produced 1.5 grams. So this is actual, produced that much with excess here. And so we don't have to worry about that. So what we want to do is find out what's the theoretical amount. All right, so we go back and say, all right, I can't go over there until I got moles. So let's take 1 gram of oxygen and turn it into moles first. All right, so that's 32 grams. Why 32? Because each one's 16. Just a reality check. So 1 divided by 32 is something. 32 invert. 0.03125. 0.325 moles of oxygen. And then we're going to convert it to sulfur trioxide. All right, we have oxygen here, sulfur trioxide here, and the conversion factors are here and here. So 3, 2. So 2 times that divided by 3 is 0.0208. 3 moles of sulfur trioxide. Okay. So now we crossed the great divide because we converted to moles first. And now we've got this many moles of sulfur trioxide. How much, what's the theoretical amount of sulfur trioxide? We need the molar mass, convert it back to grams. Right? We got moles on the bottom, grams on the top. So sulfur trioxide would be 3207 rounded off. That's for sulfur. And 3 times 16 for oxygen, which would be 48. 48 and 3207 is 80.07 grams per mole. So this is 80.07 there. We multiply that times that. I think if they're still in my calculator, I should just be able to hit one button. So that's 1.67. And this is theoretical. That's what we expect from the complete conversion of 1 gram of oxygen to sulfur trioxide. We expect that much, but that's what we actually got. Right? So percent yield is what? That one divided by this one times 100.
Where did you get 32 pounds? Oh, was that for, okay.
90%. Rounded off. Let's see what they. 89.8, close enough. There we go. Actually, I got 89.9. That's because I kept all my decimal points and didn't round off in the middle. Okay, so there's an example of a stoichiometric problem where percent yield is taken into account. We can go one step further, of course. It's not simple enough, not complicated enough yet, so let's complicate it some more. We're inching up to real world problems. We've taken all the simple mechanics, and now we're going to put them all together in one problem. So if we've got phosphorus, solid, and fluorine gas, that, by the way, should be an extremely violent reaction. Okay, what mass of P4 is needed? So we need a certain mass of that one to produce 85 grams of this one. We want 85 grams of that one, and this is actual. We want to actually collect that amount, right? But we know beforehand that the reaction is 64.9% efficient. Okay? So if we're going to work backwards from there to here, we can't do that unless we know what the theoretical is. Because the theoretical says you need to have more of this than you expect to get that with this efficiency. So what you do is you fill in the equation, right? So it's actual divided by theoretical times 100. Right? So there's our unknown. We're going to find out what the theoretical is first, then work backwards. So this is going to be theoretical comes over here, and that one goes over there, 85, and divided by 64.9 times 100. Let's see. That should work. So 85 divided by 64.9 times 100 is 130.97. Theoretical. PF3. I'm going to keep my decimals, so I'll minimize rounding error. So now that we've got that much, then you convert this to moles in order to ride the balloon over here. So this is grams of this. We need to convert that, grams on the bottom, moles on the top, to moles. So PF3 would be what? Phosphorus is 30.97 grams per mole. And 3 times fluorine, 19.00. So we need 30.97, 87.97 grams per mole. 87.97 there. Divide that into 130.97. Get 1.488. Round it off. And that's moles of PF3. Now we can convert moles of that to moles of this. So we want to end up with this one, so it's on top, this one's on the bottom, and there's one of these for every 4 of those. So we just divide that number by 4. And I get 0.3722. 0.3722 moles of P4. Okay? So we know how many moles we need to start with. Now we got to convert to grams. So what's the molar mass of P4? Well, if that's 1, then 4 of them would be 123.88. So that's the molar mass of this one. And we're going to take that many moles of P4 and convert it to grams of P4. So grams on top for 1 mole, 3722, is 46.1. Yeah, 3 significant figures. Did I say 46.1? Yep. So that is how many grams of P4 you need to start with to give you this many grams of PF3 with that efficiency. Okay, so you need a lot more than you would expect. And there's all the calculations. That's what's required in order to get the actual amount of PF3 that you desire. Okay, so between now and that's Tuesday, take a look at your homework and your review document, and then jot down questions you have for Tuesday review. Okay, we're done early, unless you have questions. I'll get this posted this evening in case you want to complete your notes.